We'll just start. Good evening and thank you all for joining us today. My name is Nagaraj Adve and I'm a member of Teachers Against the Climate Crisis, TACC. So this is actually our first talk since the latest IPCC report of Working Group 3 was released last Monday. So the report mentions carbon dioxide emissions of 38 billion tons from fossil fuels and another 7 billion tons from deforestation and land use changes. So that's actually 45 billion tons just that year, 2019, which is a lot. But where does it go? Does it remain in the atmosphere? For the last 6 decades, this share of carbon dioxide in the atmosphere has remained pretty much steady, about 44%. And this implies that the two main sinks, including the oceans, the amount that they are taking up has actually risen. So according to the IPCC's Group 1 report that came out in August last year, the ocean of CO2 has actually increased over the last half century or so. From a little under 4 billion tons of carbon dioxide half a century ago to over 9 billion tons presently. So in a sense, the Earth systems are helping us. Roughly 23% of carbon dioxide over this half a century. They also take up over 90% of the enormous heat and greenhouse gases trapped. So among the questions that are facing us today are, so what effects does this have on the wonderful oceans themselves, on us, on other species, and how long can they continue to doing so, to continue taking up carbon dioxide as they have been? To address these crucial questions, we couldn't have someone better than Dr. Roxy. Dr. Roxy Mathew Koll is climate scientist at the Indian Institute of Tropical Meteorology, IITM-Pune. He currently leads research at its Center for Climate Change Research on how climate change is contributing to the rapid warming of the Indo-Pacific region and impacts global rainfall patterns, the monsoon, cyclones, and the marine ecosystem. He's also the co-chair of the Indian Ocean Regional Panel called CLIVAR, which stands for Climate and Ocean Variability, Predictability, and Change. He's also the lead author of the IPCC's 6th assessment report. And I might also add that in addition to all this, he finds the time to collaborate with citizen science networks, with local governments, and with the media in sort of communicating climate science to society. So in that sense, sort of overlaps with what we do. By we, I mean Teachers Against the Climate Crisis, which is a non-funded and non-party organization that seeks to promote the understanding of these issues among teachers, students, researchers, and activists. Briefly about the format before I pass it on to him. He will speak, Dr. Roxy will speak for about 45 minutes and followed by a discussion or a Q&A. You're very welcome to ask your question yourself. You could key it in the chat box. If you wish to ask the question yourself, then kindly indicate so in the chat box so we could go along in the order in which the questions come. And finally, I just request all participants to mute your devices while Dr. Koll is speaking. Thank you very much again, Roxy, for agreeing to speak to us today, and over to you.
Thanks a lot, Nagraj and Aditi and the TACC team. I don't know if I can call TACC, TACC. It sounds good. It's an interesting forum. I saw some of your earlier videos as well. Good interaction and great forum. And initially, when I got the invitation, I thought there would be school teachers too, but Aditi told me it's mostly university, college teacher, that level. But anyways, I think it's the perfect forum to discuss climate change. Yeah, and probably we can have school teachers as well. Anyway, I have provided, along with all the climate change information, I have provided some tidbits which we can take to our educational institutions as well and train our students, whether they are at college level, university level, or school level, so that we can build a climate resilient future. So let me share my screen. Yeah. I hope it's visible.
Yeah, it is, yes.
So may I ask everyone to just mute your audios so that, yeah. So welcome. Here I will be talking about the ocean at our doorstep. Our doorstep. So this is a picture, of course, from Mumbai. It's so visible that we can say it's from Mumbai. We have some people from Mumbai also participating in this talk. But Mumbai is kind of representational for India on how climate change has culminated in different forms on different kind of sections of society. So on the forefront, we have the sea beating on, the waves and the water beating on into the inside of the house. And there's a person sitting there. That may be a place where they normally sit out. Maybe that's opening door to the outside. I don't know. We don't know the details. But this is one of the picture of how some of the less adept or more vulnerable sections of the society face climate change on an everyday basis. But if you go far, behind this scene to the back, you can see the high-rise buildings as well. So we see different phases of how climate change is working for different parts of the society. So whether we have a storm surge in this part or across the coast of Mumbai, maybe some sections might get affected more compared to other sections in the high rises. They may not even know about these storm surges, these huge waves that come during the monsoon, whether it's the monsoon or with the high tide, or it could be with the cyclone, these storm surges act. So let's see how the ocean is acting at our doorstep with increased temperatures. But before that, we need to know the current status of global warming, climate change. Yeah, and many of you might already know the current state. Yeah, but there is more to it, more to the temperatures if we dig a little beyond that, because we are still at the surface. We are talking about the surface. Most of the IPCC reports that we talk about, especially in the news media, what the politicians talk about, it's all about that 1 degree Celsius, 1.5 degrees Celsius, but that's the global surface temperature, global mean surface temperature. It doesn't talk about the regional implications. It doesn't talk about what happens beneath the surface, right? Of course, the IPCC reports have in detail about what happens beneath the surface, but I mean, that's many times that is lost during while communicating, lost in communication. And this is a picture from the recent IPCC report showing the global surface temperatures that we know about. And I will brief you about the axis. Of course, on the y-axis, you have the temperatures from 0 to 3 degrees Celsius. And on the x-axis, we have multiple x-axis. So we have the years over here. So now some of the years are put together, and that is according to the cumulative carbon dioxide emissions. So in the earlier period, we had a slow start. The industrial revolution started around 1850s. So the carbon dioxide emissions were small then, and the variability is also, I mean, you don't see a large trend during that period, 1850s to around 1950s. Slowly it catches up by around 1970s, 1980s, and then the temperatures. So this is the temperature change with respect to 1850 to 1900. Yeah, that is the reference period. So with respect to that reference period, the temperature, global surface temperature, have increased by about 1 degree Celsius to 1.1 degrees Celsius. Yeah, let me use the highlighter. Yeah. So you can see right now the status is 1.1 degrees Celsius. We have reached over here. Yeah. So that's with the cumulative carbon dioxide emissions since 1850 in gigatons on the x-axis. Now, what the IPCC reports and all the models say is that irrespective of the scenario we follow, irrespective of the emission scenarios we follow, we will reach 1.5 degrees Celsius in the current decade or the next. Yeah, I hope you can see my yellow scribblings, the highlighting. Yeah, 1.5 degrees Celsius in the current decade or next, whichever scenario we take. Yeah, unless we suddenly extract all the carbon dioxide from the atmosphere. And 2 degrees Celsius during 2040 to 2060. So that's like the double of what we are already facing. Yeah, from 1 degree Celsius to 2 degrees Celsius within a few decades, we will reach there. So somewhere over here. And all the impacts, the extreme weather events that we see until now is because of this 1.1 degrees Celsius. So we can't even imagine what will happen at 2 degrees Celsius. Yeah. We don't have all the information about how exactly these extreme weather events will work out. Our models are not so high resolution to say, for example, cyclones, how many cyclones at what intensity will work out. Yeah, though we have an idea, So why it is going to be 2 degrees Celsius is because the nationally determined contributions submitted via the Paris Agreement are insufficient to flatten the curve. So we might have flattened the COVID curve in some regions to some extent, India especially, but this is a curve we are not flattening in the coming decades or even the coming centuries. And there is a reason for that we are not going to flatten because of the long lifespan of carbon dioxide. And there is one more reason, because of oceans. Oceans take a long time to absorb that heat and carbon dioxide. Nagraj was talking about the absorption of carbon dioxide by the oceans, but oceans work in a time span of centuries. So centuries to even millennia probably. The temperature change that we see and the extreme weather events that we see might stay. So we need to be aware of what is happening already and how it is going to work out in the next few years. But before that, a little bit math for you guys. I think at least some of you might be teachers. Actually, I had shared this with some of my peers and friends in social media as well. So we might have people from other areas as well. But I'm not going to bore you with math. The only point here to focus is that the heat capacity, the ability to store heat or to absorb heat is more in the ocean or more for water compared to the land. That is the key here. And it's more compared to the atmosphere also. So the heat capacity or CP for water is generally 4,000 joules per kilogram per degree Celsius. Yeah, for every degree Celsius, that much heat. For rock or land or soil, whatever it is, it's about 800 joules. That's a heat capacity. So based on this heat capacity, for example, I have given an example. This based on the temperature change from winter to summer. So if the winter to summer for ocean, if it is 10 degrees Celsius, yeah, the amount of heat it can absorb or store, or the heat change is about 4 into 10 raised to the power of 9 joules. So obviously it is much larger than what is saved by the land, stored by the land. So let's forget about all this math and numbers. So basically what comes to work out here is that it's about 100 times, roughly 100 times. The oceans can absorb 100 times the heat than land can. And similarly, it can absorb more heat than atmosphere also. And one of the reasons is the chemical composition of water. We say the way the bonds work out, the chemical bonds work out, water has polarity and it has strong bonds with other water molecules. So even to change the temperature of water molecule by 1 degree Celsius, it needs a lot of heat. So it warms up slowly and it releases heat also slowly. And it saves that heat for a longer time, which is why we say water has more memory, or oceans are more memory. Yeah. So as a result, if you look at where all the heat has gone, yeah, beyond that, so this is like digging beyond the ocean surface, beyond the surface of Earth, beyond that 1 degree Celsius, beyond 1.5 degrees Celsius. Yeah? That 1.5 or 1 degree Celsius doesn't hold all the additional heat from global warming. So where has all that heat gone? Obviously, it has gone to the oceans. And where in the ocean? To the surface, to the subsurface, and deep ocean. So all that blues that you see here is where the heat has gone actually. So on the y-axis here, you have the Earth's energy budget. Okay, so we need to be at zero for no temperature change. No change in temperature means it's close to zero. It can go up and down. For no change in Earth's energy budget or no change in Earth's temperature, but that doesn't happen. The Earth has continuously absorbed energy since. So this is a plot since 1960s. You can see until 2020. So this from the most recent analysis from a paper which is still in press from Li Jing Cheng et al. And so it shows a budget of about 400 or more zetajoules. Zetajoules means 10 raised to the power of 21 zetajoules. So again, there are too many numbers here, right? So this is like, how do we equate this to something that we know? It's equivalent to the amount of heat that has gone to the ocean is equivalent to 7 Hiroshima atomic bombs detonating each second, 24 hours a day for 365 days a year throughout from 1960 to 2020. That's the amount of heat that has gone into the oceans. And if you compare it with the rest of the Earth system elements, so the ice that is here, the land that is here, and the atmosphere below, altogether it has absorbed only 7%, less than 7% of the additional heat from global warming. So oceans have absorbed more than 93% of the additional heat from global warming. Yeah, and the deep so it's most of it is in the first 100 or 300 meters, and rest of it goes below in a slow process. Even the interior ocean is absorbing on a long-term basis. Yeah, because you know the average depth of the ocean. Does anyone know? It's about 4 kilometers. Ocean is so deep, so it will keep on absorbing for centuries to come, if not millennia. And of course, we all know that it covers 73% of the globe's surface. So a lot of this heat is going into the oceans, and not only heat, the carbon dioxide as well. And if you look at the amount of carbon dioxide absorbed, we are talking about the we have been talking about the carbon dioxide absorbed by the atmosphere, and which stays in the atmosphere, which results in that 1 degree Celsius change, right? Because it traps the heat, the solar energy from the sun. Now, that is not all the carbon dioxide that has been emitted. A lot of this has been absorbed by the oceans. More than 50% of the anthropogenic carbon dioxide has been absorbed by the oceans. And where in the oceans? A lot of it has gone into the North Atlantic, because that's the area where the water sinks because the water is denser because it's colder over there. So, and when ice forms over there, a lot of salt is left behind. So the density of the water is much more higher over there. So this water sinks there, and it also takes in a lot of carbon dioxide as well. And there is a lot of, in polar temperatures, it absorbs, ocean absorbs more of the carbon dioxide. Yeah. So even the Indian Ocean also, we can see if you look at the color scale, it has been absorbing some of the carbon dioxide. This is the column inventory of anthropogenic carbon dioxide for the entire ocean depth. Yeah. And what is the impact of excessive carbon dioxide intake? So we all know, or some of us know, that if you have excessive carbon dioxide, it can change the chemical properties of the ocean. It can make it more acidic, because there is a decrease in carbonate and increase in H ions. And so and it changes the pH also. It changes the pH. So all this affects in a bad way for the marine ecosystem. So because of ocean acidification, the shell-based organisms, they are unable to make their shells, their exoskeleton, so it becomes thinner and thinner. So these organisms become smaller, and some of this might even reach extinction. So this is one kind of impact of excessive carbon dioxide intake. It also affects coral building as well, corals. And so along with temperature, this absorption of excessive carbon dioxide can create hell for these marine organisms. Now, I talked about carbon dioxide in the atmosphere, right? And I talked about how ocean is absorbing. Now, one of the things that I mentioned is that the carbon dioxide we see right now in the air, it can stay for years to centuries to more than that. Yeah. So if you look at this interesting plot here, this is from the earlier report of IPCC. It shows how the carbon dioxide in the atmosphere is absorbed and how much of it remains. So suppose the carbon dioxide we have is 100 right now. We are stopping all emissions right now. How much time does that how much time it takes for the carbon to disappear? So it takes 100 years for about 60% of it to disappear and reach 40%. Yeah, 100 years. So all of you who are listening, including me, will be gone. But even then, 40% of the carbon dioxide we have emitted until now will still remain. Even the kids that are born now, even beyond them, right? So the carbon dioxide that we emit will still remain even after 100 years, 40% of it. Now, look at the next panel. Yeah. In the next panel, you can see the years goes up to a century. No, sorry, 1,000 years, a millennia. So even after a millennium, 20% of the, more than 20% of the carbon dioxide will remain. You know why? Because the ocean, this is more from, this absorption is more from the oceans, and the ocean absorption is a very slow process. So science says that 15 to 40% of the carbon dioxide will still remain even 1,000 years from now. That is even if we stop all the emissions right now. Which is why there may not be a turning back, but we can stop things from accelerating further. We can stop things from hitting 2 degrees Celsius or 2.5 degrees Celsius so that the extreme events are not too bad. We can work on adaptation measures. Now, coming on to the ocean at our doorstep. So I'm talking from a South Asia, India perspective, because most of our audience are from India. And if you see what is affecting us most, in terms of weather changes, is in fact the ocean at our doorstep. If you look at the Indian Ocean, we would realize it's the fastest warming ocean among all the ocean basins in the recent decades. So this is a snippet from the IPCC AR6 report. It's not even finally laid out, so you can see some press marks and all, but it clearly says since the 1950s, the fastest surface warming has occurred in the Indian Ocean. So if you compare to the 1 degree Celsius, 1.1 degrees Celsius during the past century or more, in the last 65 years alone, 1950s to 2050s alone, you can see that some of these regions, some of these regions show temperatures of up to 1.2, 1.3, or 1.4 degrees Celsius. If you extend this to 2020, you can see 1.4 degrees Celsius in some of these regions. So that's a very high temperature change. We can see the entire Indian Ocean has warmed. Its red color is reaching 1 degree or above 1 degree Celsius. And this is much above the global average temperatures, particularly when we speak about global ocean temperatures. Global average ocean temperature is much lower than global surface temperatures, which include land also, because land has warmed much more than the ocean. If you actually look at global temperatures, I will show in a picture later. So the global ocean mean temperature change is around 0.8, 0.9 degrees Celsius. So compare that with the ocean temperatures here of 1.2, 1.3 degrees Celsius. Yeah. And we don't stop here. Yeah. So if you look at the figure on my on the right hand side of the slide, you can again see that so this is stretched from about 1870s to 2100, including the projections also. Yeah. So the scale is much stretched over here from 26 degrees Celsius to 31 degrees Celsius of ocean temperatures. We are not talking about anomalies here. And this here in the yellow line is observations, and the black line is the historical simulations from the same models that we are using for projections. So this change shows about a 1.2 degrees Celsius change. Yeah. But when we look at a stretched scale, this 1.2 degrees Celsius is dwarfed by the projected changes. So on a high road scenario, which we are going right now, the projected change is about 3.8 degrees Celsius per century. So we need to be at least aware of the changes we have at hand due to this 1.2 degrees Celsius over the Indian Ocean. So that's where I'm reaching at. So the ocean at our doorstep. So we have a lot of extreme weather events. Let's pick a few, and I will pick a few out of them and talk about them. Yeah. One of the most salient change or significant change in terms of climate or weather across the Indian Ocean region are floods and droughts, mostly associated with the monsoon. You can see floods happening across South Asia right now, East Asia as well, and droughts as well in these regions, especially in parts of Central and North India and all. Droughts in Africa, sometimes resulting in famine as well, and droughts in parts of Australia leading to wildfires. I even put locust swarms here. I'm not talking about it, but if you search online for it, you can see Indian Ocean warming had a role in locust swarms that were triggered in East Africa, which then went to Arabian Peninsula and then later into India an year or I think last year start. Yeah. So from there, we move on to cyclones, particularly cyclones over the Arabian Sea have intensified. Some of you might have heard about it, resulting in storm surges and all. Then we have heat waves Yeah, heat waves over the land. I'm particularly mentioning them as terrestrial heat waves. Why? Because we are having heat waves over the ocean also. Yeah. So these in fact, India is going through these terrestrial heat waves right now. Temperatures are going above 40 degrees Celsius and all. Yeah. And then we have marine heat waves over the ocean, which leads to coral bleaching and other impacts also, which we will see. And again, impacts on the marine ecosystem, these microscopic plants called marine phytoplankton, which is the base of the food chain. So I won't be talking about all these elements, but pick on some of these elements like the monsoon, cyclones, and marine heat waves. Yeah, and obviously sea level rise. Sea level rise is happening in many regions, particularly northern Bay of Bengal, which is very intense. Parts of West Pacific, East Indian Ocean region, some islands are sinking. Yeah, we will see that. So let's get into the monsoon, because that's one of the most important feature that affects the agriculture and the people of this region. Sorry. So, and when we talk about monsoon, we generally talk about the southwesterly monsoon or the summer monsoon during June to September, blowing from the greater Indian Ocean through the Arabian Sea towards Bay of Bengal, crossing land. Yeah, and this monsoon brings about 80% of the rain over India and parts of South Asia. And this is largely, to some extent, driven by, this is a simplistic mechanism, largely driven by temperature gradient, especially during northern summer. The Indo-Tibetan plateau, including the Himalayas, are warmer because of the heat capacity that I talked about. Yeah. So because land has the heat capacity of land is small compared to water, land warms faster. Yeah, and releases that heat faster also. So it gets it gets very hot in these regions, and the temperature range also is much more high. So in summer, it is that heat gradient. So this is on a seasonal scale that we are talking about, on a monthly scale. Yeah. So this land warms up, and it warms the entire tropospheric or the atmospheric column, and that creates a temperature gradient between land and ocean. The ocean is generally relatively cooler and drives these winds from the ocean to, let me see if I can show. Yeah, drives from the moisture carrying winds from the ocean to the land, right? So all this, the water we receive and the winds and all, its source is energy from the ocean. Yeah, though it's driven by the land sea temperature gradient. And if you look at the temperature changes, the global temperature changes during the last several decades, we can see that the land temperature has gone up quite faster compared to the ocean temperatures. The ocean is slowly absorbing it, but reaching there, but land has warmed much more faster than the ocean, right? Yeah. So according to this, the land ocean temperature gradient should increase, yeah, should increase and drive this monsoon stronger. So the monsoon should ideally be stronger with global warming. And also we know that as oceans warm up, there is more moisture available. With increased moisture, the rainfall is generally supposed to increase. With every degree Celsius temperature increase, we should ideally see a 7 to 10% increase in moisture and rainfall as well. But is it that what is happening with the monsoon? So let's look at 150 years of monsoon rainfall from the IMD dataset. And this is, mind you, this is the all India summer rainfall from 1870s to 2021. Yeah. I love this picture. It doesn't represent the regional variability, of course. It's part of a legacy. we have been averaging the rainfall over the entire India, but still it shows some signals. Yeah. So the blues here are the wet years when the monsoon rainfall is 10% above the mean. And the reds here are the drought years when the all India rainfall is below minus 10% of the mean. And the grays shows a normal within minus 10 to 10 deviation, right? And the red dots show El Nino years and the blue dots show La Nina years. So many of you might know that during a El Nino year, the winds are weak, the global circulation changes, and the circulation changes make the monsoon winds weaker. As a result, the monsoon rains are also weak during those years. So you can see some of the drought years coincide with this El Nino years, like this year, yeah? And opposite, vice versa for La Nina. So some of the strong monsoon years coincide with the La Nina year, yeah, like you can see over here. As a result, we have this interannual and decadal variability of the monsoon. So the thin solid line that you see here is the multi-decadal variability. So there is ups and downs in the monsoon. But if you go to the recent period, you can see a big slump over here, yeah. And we don't see any blue lines, right? Blue bars since 1998 or so on, yeah. Last 20 years have been without a strong wet monsoon. But there have been many drought years. Maybe 1/4 of the last 20 years is a drought. You can see 1, 2, 3, 4, 5. 5 out of the last 20 years are drought years. More than 1/4 or 1/3 actually, if you look at the last 15 years, maybe. Yeah. And the last year was normal. I mean, just bang normal 2021 monsoon, even that is over here. So despite a multi-decadal variability, you can see that there is a slump in the monsoon over here. And this is much more defined if you look at some of the regions. I'm not showing I have pictures of how it manifests for parts of Central India, North India, and this is much more lower. And there is a evident decline in this monsoon, but it's even visible in the all India summer rainfall, the average also, which is why I showed this picture. So what is happening over here? Yeah. I'm not throwing a lot of data and all, but let's revisit that land sea thermal gradient once again. So on the left, you have the normal monsoon, and on the right, you have the weak monsoon. Yeah. So for a normal monsoon, we need the land sea temperature gradient to work. During summer, the land is warmer, and ocean also is warm, but relatively cooler compared to the land, and that drives the monsoon winds. Yeah, and monsoon it's a complicated atmospheric circulation. So you have compensating winds in the upper atmosphere and sinking and all that. Yeah. So this is how the monsoon circulation works. But suppose the oceans are warmer and the land has not warmed that much compared to the oceans. Yeah, it weakens this gradient, and the winds also get weakened, and that's what we see. So we have more rains because the air is much more moist, but those rains we see it's happening over the ocean. So the Indian Ocean is getting more rains, and while the monsoon is not bringing as much rains as usual. So that's the story of the total monsoon rains. Yeah. At the same time, yeah, at the same time when the warm ocean is weakening the monsoon, we are having heavy rains also, and this is well evident because we have seen year after year, we are talking about floods across Western Ghats, parts of Northeast India, even Central India, Gujarat, all these regions. So all these colors, yellow to red colors that you see here over here, use my laser, yeah. So from Kerala here, North Karnataka, Maharashtra. So this is a region where we had the recent Mahabaleshwar heavy rains in Maharashtra. Yeah, Gujarat. So across, so we have the Ghats over here, and then there is an opening over here through which the monsoon westerlies manifest. So in that region, we are seeing again a rise of heavy rain events. Yeah, this is a path of the monsoon westerly. So it blows from through the Arabian Sea towards the Indian west coast. Yeah, and through the opening of the Ghats, these winds cross the Indian land and results in rains over here. Other than those coming from the Bay of Bengal as well, along with these depressions. So I'm not getting into a lot of science over here. But so at the same time, when the monsoon is weak, the same monsoon westerlies, yeah, it has resulted in a lot of fluctuations. So in a short period, we can see episodes of spurts of these monsoon winds or bursts. So for 3 or 4 days, the monsoon winds will be strong and then again weak. So on a long term during the monsoon winds are weak, but there are short episodes when these monsoon winds are strong, resulting in heavy rain events. Yeah, so that is the main crux of it. And again, this is linked to warm temperatures in the Arabian Sea, which provides excess supply of moisture to these winds. So there is, because of warm temperatures, there is more variability in the weak monsoon winds. So because of that variability, there are occasions when the monsoon winds are strong. When the monsoon winds are strong, it is carrying more moisture, resulting in these spells of heavy rains. So if I look at the rainfall change across central India, yeah. Now this is not all India rainfall, but this is a rainfall of central India. Yeah, and the gray line here, solid gray line, is a total rainfall during the summer monsoon. You can see the total rainfall is declining since 1950s until recent. At the same time, if you look at the extreme events, this is a number of extreme events. Let's forget about the valleys over here. Yeah, if you look at the number of rainfall events, extreme rainfall events, of course, it shows a decadal variability, but it's on a rise. It's on a rise, steep rise. So at the same time, when the total rainfall is decreasing, heavy rainfall events are increasing. So this is the most interesting part of or pattern of change in monsoon. So what does this mean? It means that we are having long dry spells intermittent with short spells of heavy rains. So we have floods, but the water is not able to spread out and percolate in the soil. It either evaporates or flushes out into the sea and into the rivers. So as a result, we have water scarcity, even though we have floods. Yeah. So that's the story about monsoon, a brief history of monsoon pattern change, the most significant change in the monsoon. Yeah. And from there, I would like to shift a bit more into the oceans and then again come back into the atmosphere and changes over the land. So one of the interesting events, extreme weather events that has been happening, especially in the recent decades, are heat waves over the ocean. We have heard about heat waves over the land, but here I present you heat waves over the ocean. We call it marine heat waves. Sometime back, somebody asked me if heat waves are like waves. Are they like waves traveling over the ocean? No. These are just patches of warm water over the ocean, extreme warm waters over the ocean. Yeah. And if the normal temperatures are like 26, 27 degrees Celsius, this could be like 30, 33 degrees Celsius or more. Yeah. And you can see that here. So let me explain this figure first. Yeah, it's very easy to decipher, very easy to understand. On the y-axis, you have temperatures from 28 to 32 degrees Celsius. So the average, these are temperatures average over Bay of Bengal during April to May 2020. Yeah, and the average temperature here should be around 28, 29 degrees Celsius or slightly above that. That's what is shown by the blue line over here. Yeah. And the green line shows the 90th percentile. Yeah. So whatever happens over the 90th percentile is the top 10% of temperature events. Yeah. And marine heat waves are those periods of extremely high temperatures in the ocean above its 90th percentile. Yeah, above this green line. So what happened in April, May 2020? These are temperatures were going from 29 degrees Celsius to, again, it was peaking and then it went above the 90th percentile. And it lasted for almost a month, mid-April to mid-May, right? Extremely high. And if you look at the deviation or the departure from the average temperatures to the peak, it's about 2 to 3 degrees Celsius, right? So that's a huge temperature change for the ocean. And this for a regional average, if you look at one location, one grid point in the ocean, it could be like 3 or 4 degrees Celsius or more. And look where the temperatures are reaching 31, 32 degrees Celsius. These are record temperatures in the ocean. So look at the spatial patterns over here, around the same time, April, May, average conditions. So you're on the rightmost, we have the color scales. So the temperatures should be ideally between 29, 28, 29, 30 degrees Celsius. And some patches you can see warm temperatures. But during marine heat waves over the same time, you can see temperatures crossing 31, 32, 33 degrees Celsius, right? Extremely high temperatures over most of North Indian Ocean, including Arabian Sea and Bay of Bengal. So these kind of events can cause marine habitat destruction due to coral bleaching, seagrass destruction. It can result in, it can affect the fisheries as well, drastically. Yeah? And the largest impact is obviously on corals, the impact that we knew until recently. So why corals? And why should we focus on corals? Corals occupy only 0.1% of the globe surface, 0.1% of the globe surface. Yeah, but 25% of the marine ecosystem or marine biodiversity are directly dependent on corals. Yeah, especially on the corals in the Indo-Pacific region. We have a coral triangle in the West Pacific, Indo-Pacific region, which has most of the biodiversity in the global oceans. Yeah, and corals have, we see these colorful pictures, colorful pink colors of the coral. Yeah, this is from a documentary called Chasing Coral in Netflix. Yeah, these colors are provided by a mucus membrane on the corals. Yeah, it's called zooxanthellae. It acts as its shield and gives the color. And when we have warm temperatures like marine heat waves, it bleaches it away. It peels that zooxanthellae off the corals. So that's what these very extreme high temperatures have. And this is happening in Gulf of Mannar, along the coast of India and in the Indian Ocean region. We have only few coral reefs. Like in Gulf of Mannar, these marine heat waves have been happening in the last several years, and when these heat waves happen year after year, it kills the corals. If it's only 1 or 2 heat waves, corals can revive themselves, but year after year it happens, there is no scope for revival. It leads to coral mortality. Yeah? So that's about corals, and that's what we knew until recently. But now science shows that corals can no, not corals. Marine heat waves can lead to impacts on the atmosphere also. So so here I have put an icon of cyclone, where the cyclone often occurred in Bay of Bengal during April, May. So cyclone often, it was an extremely severe cyclone. It occurred in the mid-May time. It occurred at the peak of this when the marine heat waves happened. Yeah? You can see as soon as cyclone often occurred, there is a dip in temperatures. So again, yeah, there is a dip in temperature, right? About 2 degrees Celsius or more. But even with that dip, you can see that throughout this period, mostly the temperatures are above average, and most of the period, the temperatures were above the 90th percentile. So why cyclones? Before we get into in detail about cyclones, let me show what the buoys are instruments in the ocean. So the earlier pictures, the temperatures that we saw were satellite estimates, average over a box. Now, if you look at temperatures from instruments in the ocean, we call them in situ instruments. Yeah, this is from the Ministry of Earth Science, NIOT and INCOIS. So we see temperatures reaching, crossing 32, reaching up to 34 degrees Celsius. 34 degrees Celsius as an oceanographer in the open seas. These are record temperatures that we have never heard of. Yeah. So Bay of Bengal recorded surface temperatures of 32 to 34 degrees Celsius just before cyclone now. So that is, and which shows that we need more of these kind of buoys and instruments in the ocean. We lack these kind of instruments in the ocean. There are a lot of gaps in the ocean. Satellites alone cannot detect the high values of record values of many of these temperatures. So we need to invest more in these kind of instruments to understand these kind of marine heat waves. Yeah. So coming to cyclones, like I mentioned earlier, a lot of heat is absorbed by the oceans. Yeah, and these warm waters are energy source for cyclones. We know that cyclones form over the ocean, right? Why is that? Because the warm waters in the tropics, they provide the heat and moisture for cyclones to form, for the convection to develop across the troposphere for about 12 kilometers height. So as the oceans warm, it provides more heat and moisture, and it drives more cyclones. These are the cyclones which happened last year, back-to-back cyclones just before the monsoon. And monsoon, even the monsoon onset time, they are not favorable for cyclones to form, because we have those summer monsoon winds in the lower atmosphere, but the winds in the upper atmosphere are in the opposite direction, northeast. So winds in opposite direction prevents the vertical formation of cyclones. We call it the wind shear. So such kind of wind shear, or generally the monsoon conditions, are not favorable for cyclones. Even the onset conditions are not favorable. But because of incessant warming, this convection is able to break through and form cyclones very close to the onset period. That's what we see with Cyclone Tote and Cyclone Yas. Now, I have put this left and right for a comparison later. So Cyclone Tote was an extremely severe cyclone of 220 kilometers per hour. You can compare it with your car speed of 60 to 80 kilometers, maybe. Gas cyclone, 110, moderate cyclone, right? Yeah. But if you see the destruction it has caused, maybe on our doorstep, it's different. So if you look at how the cyclones have changed over time, this is a comparison between different decades. Here, 1982 to 2000 and 2001, the recent decade. We can see that the largest change is actually in the Arabian Sea. One of the reasons is Bay of Bengal traditionally or historically has been a warm ocean. Bay of Bengal has been a warm ocean. So about 3 to 4 cyclones, 2 to 4 cyclones per year used to happen, and still happens. There is only a slight decrease. Yeah. But if you look at the Arabian Sea, a few decades back, the Arabian Sea temperatures were cooler. It was below 28 degrees Celsius, which is not that conducive for cyclones to form. But in the recent decades, it has warmed up, supporting more cyclones. So there is a 52% increase in cyclones during the recent decade. Excuse me, drink some water. I hope all of you are there. I would love to hear some voice.
Yeah, Dr. Roxy, actually, I was just going to come in to say, maybe we wind down about another 7, 8, 10 minutes. Would that be okay?
10 minutes. Yeah, fine.
Yeah. 8 to 10 minutes would be good, yeah. Thank you.
So it's not just the number of cyclones that have increased. Yeah, there is a 150% increase in the number of very severe cyclones. The cyclones that have increased are mostly very severe in nature, and the duration of cyclones also have increased 80%. Sorry. There is an 80% rise in the total duration of cyclones and intensity as well. Yeah. Another feature, another change in the feature characteristics of cyclones are some of these cyclones are intensifying quite rapidly. So cyclones, sorry. So cyclones are intensifying in quite a short time. So when you go to sleep, you are seeing that the cyclone is it's a weak cyclone of 100 kilometers per hour. But when you wake up, your roof is already gone because the cyclone have overnight, the cyclone have developed into a 250 kilometer per hour cyclone. Yeah. And there are multiple events, multiple factors of a cyclone that compound this event. One is a storm surge. So here is the wind, the waves due to the strong winds. On the y-axis, we have the wave height. Once, I don't know why my marker is not working. Yeah, so that's the wave height. You can see waves up to 5 meters. This is all the Mumbai coast during Cyclone Tote. But over some regions, the waves are much more larger because the slope of the continental shelf and all is different from what we have in the Arabian Sea. So there are larger waves of up to 10 meters or 11 meters. This was detected by buoys in the Bay of Bengal. Yeah. So such huge waves can splash in a lot of water onto the coastal region, flooding the coastal region. Yeah. And another factor that is compounding here is obviously the sea level rise. You see a picture of a cute rodent here. That's a bramble K. melami. It's the first mammalian species to be extinct due to sea level rise and inundation. Yeah, it happened in the fringes of the Indian Ocean over here. It's a small island where this mammalian species was endemic. And it's not just the fringes of the Indian Ocean. This is in Bay of Bengal, the one island. It's a disappearing island. You can see the aerial picture from a few decades before. And now this island is disappearing, right? So the sea level rise, along with other factors, is compounding the impacts during a cyclone also. So here I show two events, Cyclone Tote and Cyclone Yas again. So just a moment. I'm trying to do this. Yeah. So this is a video from Cyclone Tote on the west coast from Kerala. You can see the storm surge pushing a lot of water, flooding the coastal region. Right. Now let us look at Cyclone Yash to the right. Remember, Cyclone Yash was a moderate cyclone. But you can see the water is flooding inland several kilometers. It actually went up to 60 kilometers, that's what I heard. So what happened here despite it being a moderate cyclone? So one of the major impacts here was multiple factors overlapped here. Yeah. So there was storm surge due to the cyclone. Cyclones are bringing more rain. So the rain, it's adding upon this storm surge water. Yeah. So it's like double flooding. And the sea level rise over the Bay of Bengal region is much more higher than the other regions due to multiple factors. I'm not getting into the details. It all coincided with the high tide. So the flooding was much higher. The salinity intrusion went up to several kilometers inland, damaging the agriculture over those regions. We call them compound floods. These kind of compound events are increasing. We know that they are happening, but we are unable to quantify it. Now, if you want to understand these kind of events, yeah, we need data from different departments. The rain data might be from the Met department. Sea level data maybe from another department. Now, water level data might be from the Water Commission, Central Water Commission. But we need administrative information also about the local topography. To understand these kind of compound events, we'll need interdepartmental cooperation and research as well. Yeah. Another example of a compound event is the recent Maharashtra floods. Now, this might look simple. We had floods over the Mahabaleshwar region in the Ghats. I think it's what Vasishti, I forgot the name of the river, Vasishti River. It took the water to Chiplun, flooded that region. One of the biggest floods. I don't know if it had ever recorded such kind of floods earlier. Yeah. Now, if you look at the rains itself, we have some stations in Mahabaleshwar and showed record rains almost in the 22 to 23rd, 1 liter, more than 1 liter of rain per square meter in 2 days. Yeah. So that's like huge amount of rains lashing down. So it went downhill. Now we might think that's the reason for all the floods, but we should account for the sea level rise on the west coast. You can see on the west coast, and it coincided with a high tide. So the water was not flushing out from the river at the same time. Yeah. On top of that, there were reports that there is river encroachment in Chiplun and other areas. Yeah. So what happens with this river encroachment? So there are multiple factors compounding these events. So it's not just climate change. That's one of the message I wanted to say. So generally we have meandering rivers like on the top, and when there is heavy rains, we have floodplains on the sides of the river, absorbing and spreading out this water. So the river comes back to its normal level soon after the extreme weather event. But we are trying to shape the river, shape the meander, and concretize the floodplains. There are no more floodplains. So when the river overflows, it floods. There is no space, there is no floodplain for the water to sink. So climate change is not the only culprit, and this is where we can work also. This understanding of this kind of compound events is the solution that that we can work on. Yeah. So though we see that climate change is presenting all these kind of extreme weather events, yeah, it's easy for us, and in India we see very often to put the blame on climate change, on rains and all. Of course, rains have increased, floods have increased, droughts have increased, but there are ways to manage it. And this is coming full circle on the Mumbai picture. This looks very beautiful. Those blue colors that you see are actually tarpaulin roofs. These people do not have tarpaulin. They do not have proper roofs. So when a cyclone or heavy rains lash, when the high tide occurs, many of these areas could be submerged. We don't know whether their roofs are blown away first, or the floors get, or the ground gets flooded first. And at high rises, we may not even understand the impact of this kind of events. And can you actually spot a river? So let me use my highlighter. So what you see, this line is supposed to be the Miti River crossing through this. Yeah, it is not a river anymore. It is supposed to flush out that excess flood water from Mumbai into the Arabian Sea. It's not even a nala, it's not a canal anymore due to encroachment. And these are regions where we used to see decades back mangroves. Probably there are no mangroves which can absorb these kind of floods.
Dr. Roxy, I'm sorry to interrupt again, just to be allow time for questions from the participants. Could I ask you to sum up maybe in 2 or 3 minutes?
Yeah,
Sorry.
perfect. I just have, I think, 3 more slides, which gives the essence of it, and then we will wrap it up.
Yeah, right. Thank you.
Perfect. So I talked about there about ecosystem-based approach. So we have multiple ways to, treat these scenarios of sea level rise and floods, but IPCC and other studies shows ecosystem-based approach is the best. And schools and colleges are best way of, climate change-based education and learning. So I'm not getting into the details of it. So whether it is floods or droughts, tropical storms, there are multiple ways that students get impacted. It can cause to injury, health impacts, reduced access to safe water, livelihood impacts. So identifying these solutions are, identifying these issues are important for providing solutions. And when we work on solutions, it can be on government scale. Government includes a climate change strategy for education sector. It can be included in the curriculum. Teachers can receive training in climate change and also disaster management. Yeah, and it's applicable not only for schools. So whatever table you see is for schools, but it's applicable for universities as well. Yeah? And this is an example on the right. We have examples on how it can be incorporated, or it's already getting incorporated in some of the school materials at different scales. And there are multiple ways we can work on it. This is my second last slide. I have just one more slide, I think. Yeah, we can work on access to drinking water. We can work on solar panels. Any new educational institute that is built should have a solar panel. It should be, so we will, and it should have water harvesting as well. So that will take care of the water security and also the energy security of the institution. And that's one way of being carbon neutral as well. Yeah? There are examples from some states which have already worked on this. And I have my own example of working with Citizen Science Network and schools. So this is a school. This is my example of a solution, how a solution has worked out. This is a school very close to where landslides and heavy rains occurred last year. Lives were lost for some of their friends. And last year, almost 1 year ago, they installed a rain cage in their school premises, and they started monitoring the rain. And recently they published a book on rain data for the last year. They were very happy. They were also monitoring the river nearby, making sense out of the weather and climate variability. So this gives them a sense of how precious water is and how preciously we need to treat water. They are trying to understand the climatic changes also. And they're trying to have a water harvesting system. So they are connecting all these elements together. So perfect example on how climate education can be weaved into the curriculum and activities. Yeah? So if we can have all that together, a collective effort, we can have a climate resilient future. With that, I stop today's talk and happy to take discussions and questions. I see that there are a lot of comments.
Yeah, thank you so much, Roxy. I was so reluctant to stop you from speaking. It was so lucid and communicative and fascinating. And others, I really didn't wish to stop you. Yeah, there already are a number of questions in the chat box. And like I said, please put your questions there, or feel free to, if you wish to ask Dr. Roxy directly, just indicate in the chat box if you can. I want to just sort of abuse my position as someone chairing and ask a question and jumping in first. If you don't mind, Roxy. So just going back to the initial part of your talk, about the absorption of carbon dioxide in the oceans. And ever since I've been engaging with climate change 15 years ago, I've been reading about whether there might be limits to that. I mean, how long can the oceans continuously keep on picking up the additional carbon dioxide that we keep throwing up into the atmosphere. And in fact, last year's IPCC report talks about a hiatus in the 1990s of the ocean's uptake of carbon dioxide. So is that true? And one, secondly, is there any explanation for that? About why that hiatus, why the slowing down of carbon dioxide absorption is happening? Is it just random variability, or are there the reasons in the literature, in the science about why it might be happening? Because its implications are really quite worrying, let's say, if the oceans take up less carbon dioxide than they have been.
Yeah. So the hiatus you are talking about, so there was a hiatus which was famous sometime back. It was about global temperatures like temperature rise.
I'm not referring to the 1998 hiatus. I'm referring to the carbon dioxide uptake.
Got it. Yeah. So anyway, I'll keep the answer very simple for the audience sake. And so one of the major thing is that if the ocean is warmer, then the carbon flux intake is much more less. So that is the basic condition of how with increased temperatures the ocean refuses to take more carbon dioxide. That absorption is lesser as time passes by. So we might have only a few more degrees until when the absorption that we see right now continues, and after that the absorption rates might go down further, so the amount of carbon dioxide in the atmosphere will be much more. Yeah. And also in events like as this ocean circulation also is it also responds to these oceanic changes, atmospheric changes, and also the atmospheric circulation also changes. So we can see that as a response to these circulation changes also, there is less absorption or sinking of carbon dioxide in some of the crucial areas like the North Atlantic that I have shown. Yeah. So I don't know by when that might happen, because I'm not an expert on that. But one of the major factors is the ocean. As ocean warms, the absorption rate goes down, and also the circulation also is hit by ocean warming. So there is less sinking of carbon flux due to that.
Yeah, sorry to interrupt the discussion. The fact that we have major ice sheets melting and disturbing the salinity, I'm guessing even that would have an impact on how much oceans can absorb. Do we have a relation or a quantitative connection between the two? Has that been established?
Yeah, I think so, because ice melting and then that even ice formation and ice melting processes have impact, especially on the northern latitudes, on how the ocean circulation works and sinking as well. But I don't have a clear understanding of that, how exactly it quantifies it to the absorption rates.
We'll now go to the question in the chat box, Dr. Roxy. So Professor Barbara Harris-White asked a question based on her own observations in Arunachal Pradesh and parts of the Northeast, where she says she's the lowest readings of fewer extreme events in Arunachal. And if so, why is that? Is it because of fewer observations? And does that reduction in extreme events extend beyond over the hill region called Zomia, to the south and east of Arunachal, that is in Burma and in Yunnan? It's a question. Top of the chat box. Yeah.
So that's a very regional specific question. So I've seen that in the Northeast, some regions the extreme events are increasing, and some regions it is not. So it's like partially part of it, especially towards the Assam region and all, the extreme weather events are increasing. So it might be the way how the westerlies, the monsoon westerlies, are interacting with the topography. So we have seen that the role of topography, how the hills and valleys and the topography is, and how they interact with the westerlies are interacting with the way the extremes are also acting. Like I am from Kerala, so I have observed some of the Kerala floods and heavy cloud-burst kind of events in Kerala. And I've seen that most of these extreme weather events, heavy rainfall events of 200 millimeter per day or 300 millimeter per day are occurring over the hilly areas. So where orography interacts with the moist clouds and all. So this might relate to how topography interacts with the localized convection, along with how the westerlies act there. Yeah. And in terms of Himalayan regions, one of the trends that we have seen is that over most of the Himalayan ranges, the snowfall has reduced, except some particular regions. Snowfall has reduced, but the rainfall, the total rainfall has increased. So less snow, but more rains. Yeah. But if you are talking about very specific region like parts of Arunachal, then we will have to do in-depth research on that. Yeah, we do have data for that. You might need somebody to pick up that region and see how it correlates with the depressions from the Bay of Bengal, the monsoon westerlies, the topography, and all that.
Raghu, I notice you have a number of questions for Dr. Roxy. Do you want to come in yourself, or would you like me to read it on the chat box?
Yeah, thanks a lot.
Yeah, turn it. Yeah. Sure. Yeah.
Put them on the chat box. Very nice talk. I enjoyed the colorful slides and beautiful graphs. Yeah. So my question is, I've always been asking that in relation to the effects of climate on various ecosystems, there is always excessive emphasis on carbon, justifiably so, but there are also other greenhouse gases, and in the case of water there are other species like nitrates, phosphates, sulfates, which contribute to acidification, they contribute to biodiversity changes. So
yeah, true. I see that question. So yeah. Definitely, especially along the coast, both over the west coast and east coast, particularly over the west coast near Maharashtra, Gujarat, and all, we see that the effect of nutrient inflow through the rivers and other flush out points are quite large. Not only in terms of polluting the coastal region, but also interacting with the acidification, biodiversity, and also it's some of these changes in nutrients are resulting in harmful algae blooms. Yeah. So so instead of having those normal marine phytoplankton and marine algae, we are having more of harmful algae, and we are also seeing other change in species as well, and this might be a combination of multiple factors. So I talked about compound events. So this is another factor compounding to these impacts. So we see fishes migrating from the surface levels to deeper levels because of temperature, and also from from near equator to poleward. So in a similar way, that temperature is affecting these influx of nutrients and pollutants from land, also is definitely affecting them as well in the biodiversity.
So how much do we know about what is the proportionate contribution of water pollution to all these changes, and what is the contribution of pure global warming, essentially radiating from the air? So no chemical contributed to water directly other than carbonic acid, perhaps.
Yeah. I get that point. So that kind of studies, specific studies have to be done, actually, have to be taken up. It needs multiple departments to work together. There should be interest in that. There should be, probably universities and institutions can take it up. because the problem with institutions like ours is like that it is focused on a very particular mission, like on monsoon. So these kind of institutions may not pick up this kind of research. So we need interdepartmental research activities which incorporate this kind of.
In a way, the risk of attributing whatever we see happening in the air or in the oceans to climate change
True.
alone,
Exactly.
and running the risk of ignoring some of the other land-based events which may not be directly related to climate change. So we are running that risk to some extent.
Definitely, and that's what is happening over the Western Ghats also. When we have landslides, we right away blame on rains. Yeah, that's an easy blame to be put on. But other factors like how we are changing the landscape in terms of land use, land changes, deforestation, quarrying, mining, all these factors are also part of this. So just like that, over the ocean also a similar story.
Thank you very much. So last question is, when we talk about the role of nitrogen in nitrous oxide and other reactive nitrogen species in climate change, the general dismissive approach is that these are very short local radiative forcing effects. They don't really matter in the larger picture. Do they matter much more when it comes to the water and aquatic and marine effects more than the matter in the air and stratosphere?
Well, that's an interesting question. The way, so we are talking about, if you talk about other greenhouse gases like methane and nitrous oxide. So one thing that sets them apart from carbon dioxide is like methane have a high potential for absorbing solar energy, but then the lifespan of methane is relatively short. So if we stop emissions, methane emissions, or if we work on methane emissions, we can kind of regulate it to some extent. Yeah, but the impacts on water column maybe not that understood. Yeah, there are some studies on how trace gases like this interact with the ocean surface, but we don't even have proper measurements of that.
So the apportionment of various positive factors is still a very open area.
What's that?
The apportionment of various factors that contribute to the current trends in the oceans that you are talking is still pretty much an open area. Of course, one big factor is the climate change, but there are probably other probably small or big factors which we are yet to determine and put a number to their proportionate contribution.
Yeah, so to a larger extent, we are able to identify the larger driver, but the other factors which can cumulatively make it worse, we don't even have the data.
All right, there are other probably people waiting to ask their questions.
Yeah, I'll just bring in.
So I'll leave it there, and you can comment on the ecosystem-specific standards if they exist and if not, why.
Just Raghu, let's just take a question from Lavanya first, and then you can come back.
Problem.
Okay,
I'm done.
Lavanya Suresh is asking Dr. Roxy whether you could go into spell out the multiple factors underlying sea level rise.
Yeah. That's an interesting question that, I didn't want to get into the details. So when we think about sea level rise, we might think that it is rising evenly, uniformly across the global oceans. We might think it's happening just because of the ice or snow melting in the polar regions, Arctic and Antarctic, and in the Himalayas, glacier melting. But that's only less than part of the story. So if you look at the sea level rise, so if you look at the sea level rise, more than 50% of the sea level rise, especially in the Indian Ocean, is due to other factors. One of the major factors is thermal expansion of water. So when water warms up, we can imagine the entire water column. It's all warming up, right? When water warms, it expands. And Indian Ocean already has the warmest waters and it's warming at a faster rate also. So the expansion rate of water in the Indian Ocean is much more larger. So we call it thermal expansion. So other than melting ice, water adding the volume, yeah. So the volume is increasing because of thermal expansion also. So this is a major contributing factor. About 50% of Indian Ocean sea level rise in the Indian Ocean is due to thermal expansion. Now it doesn't stop there again. If you remember, I told you about Bay of Bengal sea level rise. It's much more higher compared to other regions, which is why the impact of cyclone storm surges, flooding and all is much higher there. One of the reason is parts of that region, northern Bay of Bengal coast, including Bangladesh and all, it's gradually sinking on geological time scales. So it's sinking at few centimeters over decade time scales, yeah. And because of that, the impact of the sea level rise is much more higher in the northern Bay of Bengal region. So you can see that all these multiple factors are affecting here, yeah, in terms of sea level rise. So that is why if you look at sea level rise at one coast or one region, the sea level rise is much more than the other region. So it's all non-uniform, it's uneven sea level rise. Thank you.
Do you want to ask the question now or later? You said you want to ask at the end, or do you want to come in now?
Yeah, I mean, I have a follow-up related to this answer which Roxy gave. So I have another question which I can ask later also. Is that okay? You have time?
Okay. We got a couple of questions here from Alka.
I'll wait then. No, not a problem. I'll wait.
Yeah. All right. So there's a question from Mayank and from Alka Dameja, which in a sense are related. So Mayank asks actually about the end of your presentation, which I unfortunately cut short, Dr. Roxy. About the issues of mitigating emissions, the question of mitigation itself, which is the subject of this latest report by IPCC, and participation. So could you sort of expand that a bit? And we have a sort of linked question by Alka, a longish question where she says much more needs to be done. What kind of friendly solutions foresee for India, where the vulnerable and disaster-prone areas?
True.
Yeah, cut a question short in the interest of time.
So the most important point here is that while climate change is global, we think of climate change as a global thing, but the impacts are always local, very localized impact. So the impact that Mumbai has is totally different from another coast like Odisha or Kochi has, or Kolkata has. It's totally different. And even on the Ghats area, it will be totally different from what region like Mahabaleshwar in Maharashtra has with other regions in Maharashtra, right? So the impacts are always local. So the measures of adaptation are also local. The problem is when we talk about mitigation in terms of reducing carbon emissions and all, it is beyond the scope. I mean, to some extent, it's beyond the scope of an individual or even a panchayat or a district or even state sometimes. We need a global effort to reduce emissions. Yeah. So the question is always what as an individual, as a citizen, or even as a panchayat or as a village, what can we do about it? So most of the answers or solutions are from an adaptation point of view. And many times we wait for a national climate change action plan working from top order down, but that may not work all the time. And that may not be because your impacts and how it works out are local. It may not, that may not be effective for your region. So what we need is a local, localized climate change impact and environment assessment for each region. And we need to disaster-proof each village based on this assessment, a micro assessment and disaster-proof based on that. So to some extent, like many departments have information on landslide-prone areas, flood levels and all. If we have that, well and fine. We need to sit and look at it and see how this is changing. And based on that, we need to have local plans. And that is where citizen science networks how can work. The example I gave was from a school point of view, but it's actually a part of a large citizen science network in Kerala. So it is based on a river called Minichil River. I'm giving an example here. So it's a 70-kilometer river, kilometer long river from the Western Ghats region, from high range to mid range to low range, where it flushes out into the Arabian Sea. So across this region, citizens, people like, just normal people from different wakes of the society came together because the river is changing, rainfall is changing in that region. So, so they made a Minichil River Society. The river is called Minichil River. They made a Minichil River Protection Council. It has been there for several years, and in the recent years they started installing rain gauges. Now, rain gauges are a very cheap solution to understand, because first thing is to collect data. If you don't have data, you cannot manage it. You need to have data so that you know how the rain changes. Like for a national agency like the Met Department, the maximum reach it has is at a district level. Even at district level, it may not have a rain gauge or a temperature sensor. It may not have data. So we need to work on that local panchayat level or very localized level to have these rain gauges installed. I'm giving an example because flood is a important extreme weather event affecting across the country. So citizens came together, they installed rain gauges at different locations like schools, colleges, at their own premises of their own houses. Now they are able to monitor the rain and its changes. So what happened in 2019 when one of the floods occurred? Just before the floods occurred, there were heavy rains in the high range. Extremely heavy ranges of maybe 150, 200 millimeter rain or more. I don't remember exactly, but they know that within 2-3 hours downstream, the river will be flooding. So they alerted a community which of migrant workers, I think, of a colony which was in the banks of the river Minichil, and they alerted them that within 2-3 hours the flood water might come. But the colony residents were not ready, because when they see the river was not flooded, but the authorities they pushed the warning again, and they evacuated the people. 70 families were saved because that region was wiped out with the floods in 2-3 hours. So this is an example on how localized activities can come together collectively. Now panchayats have taken it up. Now it is setting an example. You saw the book from the school. So this is a perfect example of how citizen science networks can work. Take it as a model for other regions also. I can talk on more and more, but I don't want to work on that. But UNICEF also is working on schools on a similar line based on this example.
I may take the liberty of putting in Professor Roxy's website in the chat box. I've just done that. If you press the link, it has
thank you.
Work that he's just talking about in the river citizen science efforts, but also his papers and the work of his center, which actually is quite remarkable.
Thank you. Actually, some of the research and news and details of those efforts can be seen on that website. Thank you.
Right. Yeah, it is quite, but it's a remarkable website. Yes. Mayank, I noticed you have a specific request about an earlier slide. Would you want to take that forward, or shall we? Or are there any further questions? And if there are not, then I just like to say thank you. That link actually also has two of Professor Roxy's very recent papers published in 2022, if I'm right, here on cyclones and on marine heat waves. I know that was just downloaded just today, and they seem really both interesting and important. If you want to share anything in particular about it, I would like to say, how much it's been such a pleasure to finally have you speaking here in this series of TACC, Roxy. I must say, I've just benefited from your papers over the last several years, and they really are quite remarkable. I would urge everyone to take a look at his writings, both academic and in the popular domain, because he also does write, and in fact has written after the the earlier IPCC report. Yeah, and that's also there on that particular link. So, Dr. Roxy, thank you very, very much for coming and speaking to us today. And I can't tell you how both interesting and lucid your presentation was. And with your permission, it will also go up on our site and it will be shared, quite widely. Really, thank you very much once again.
Definitely, Nagaraj.
Yeah, do
And,
stay in touch. And, yeah, please.
Yeah,
Please come
thanks for this, opening up this forum. I'm sure it might have inspired some of you. We are thinking of coming up with, guidelines for Citizen Science Network also, so that people like you can be part of it. We need teachers and all other citizens to be part of it, science-aware people to be part of it, so that we can extend this kind of work across India, across South Asia. This is a region where we need to work on, adaptation measures at local level.
Absolutely.
So each local, that hubs can work on. I mean, the impacts are totally diverse. So we will have totally diverse set of challenges to take up. Yeah. Thanks a lot.
Aditi had a question. Did you want to come?
I can get back to him later on. I have his personal.
Yeah, we'll see on a glass of beer.
Yeah, I'll get back to you. Maybe we can have a proper discussion session sometime.
Sure.
Okay. Yeah.
Thanks a lot. Yeah.
Thank you so much, Roxy. Yeah. Let's carry on that last bit of the conversation forward.
Yeah.
Yeah. Right. Okay. Once again.
Thanks a lot. Good night to all. Bye-bye.
All right.
Thank you for this, Roxy.
Bye, Nag and Aditi.
The call.